Well, maybe I'll go ahead and jump in. So actually, if I could ask people here to be pipe down for a minute, I'm going to do the introduction over Zoom, and then we'll be back. Then we'll be watching on here. And I apologize, the sound. Randy's working on a workaround, but we may be just listening to my laptop sound. We get the big screen, but the little sound. So we'll see how that works out. So then for everyone, yeah, thank you for joining our Repowering the Kenai event. We have it's a little bit of an experiment in hybrid events. I'm actually going to okay. It's an experiment in hybrid events for us. So we do have several in-person events. One here in Soldovia. Scott is in Homer, where he'll be presenting from, and then we have Lori in Seward, and we have Ben in Soldotna. And so the idea is we're gonna join Scott's presentation here in a moment, and then after about an hour, we'll let enough time for questions and stuff. Then we'll go and adjourn to our own in-person events. And so here in Soldovia, I know we're going to be discussing heat pumps and some of the details around that. And Scott nicely sent me a little introduction so that I actually can say something here, because Scott and I have been working together in a few different places, including on the Resilience and Security Commission board, and so we've gotten to know each other there. And yeah, just a fantastic font of knowledge on this whole topic. And he started out, or he's retired from the Alaska Housing Finance Corporation, and brings a lot of knowledge from that experience. So Scott has worked in the building science energy efficiency realm for over 30 years. He managed the home energy rebate program and the Alaska Energy rating system until he retired in 2018, and he's chair of the Resilience and Security Commission, and really looking forward to to hearing his presentation today. And yeah, thank you all very much for joining us.
Okay, well, thank you very much, Abe. So we're here to talk tonight about the building, what happens in building flows, heat, air, and moisture. And okay, we'll get this working here. But to preface all this, we have an issue going on here in Cook Inlet, and I happened to attend the Alaska Sustainable Energy Conference in May that was sponsored by Governor Dunleavy. And one of the people that the governor invited was Luc Sargé, who is the vice president of operations for Hilcorp. And Luc got up and he said, "You should buy less of our gas." And Hilcorp supports any and all diversification of energy diversification for Cook Inlet. And he said that we have no problem meeting our commitments for the next 5 years. And if we act with a sense of urgency to diversify our energy sources, we can overcome our lower gas supply. Well, so one of the interesting things is that Hilcorp supplies all of the utilities along the rail belt, either directly or indirectly, with natural gas. And these contracts are all expiring before 2023. And Hilcorp has told all of the utilities that they don't think that they're going to be able to renew those contracts at the same level that they currently are. So put that in context for the rest of our evening. So this chart is basically showing that we have the first contract, this purple one here, is expiring in 2024. And that is Homer Electric Association. That may be a little close to home, but so Homer Electric Association at this point does not know where they're going to get gas to supply electricity from in 2 years. Just a little bit of context. A lot of the other utilities, they have a little bit of gas contracted out to about 2028. And Chugach is about in the same place. Chugach is a little bit better off because they got their own gas field that came with the purchase of Municipal Light and Power when they bought that. And only NSTAR goes out to about 2033. So we have issues coming up. So this is the context for why we're having these conversations tonight. So what can you do in your own home? In our homes, our house is a system, and they're made up of all these different systems. We have the envelope and mechanical systems like the plumbing and the electric and the heating systems and whatnot. We have different things going on, like things that we want to have in our homes. We really want comfort. We really want not to have to put out a lot of money for repairs and operations, and we want it to be affordable. We also definitely need them to be healthy and safe. And what's going on in there to affect all of this is heat, air, and moisture, and that's what we're mostly going to be talking about tonight. So we're going to talk a little bit about Mama's house. This is the house that I grew up in Massachusetts, and it was built in 1941, and it was actually, the energy cost at the time was too low to even be considered a big deal, right? So that was not really much of a problem, but there's a couple of things that we need to know. Just some basic physics. I'm not going to bore you with a lot of detail, but we do need to know that heat moves from hot to cold, and it moves equally in all directions. Now, you may think that heat rises. Well, not really. Heat flows in all directions, up, down, left, right, sideways, in, out, but warm air rises. So warm air is more buoyant and less dense than cold air, so warm air will rise. And whatever warm air rises to the top of the building, it leads through cracks and crevices and things that I'll show you a little bit further on. And whatever air is leaving that building is being replaced by cold air that comes in on the bottom. So there wasn't a lot of problems with this until about 1973. And in 1973, the Arab oil embargo came about, and energy prices about tripled in no time at all. And some of you may remember, if you've got enough Arctic blonde in your beard or hair, you may remember gas lines where you had to either go odd or even days to the gas station. And energy prices about tripled at the time, including the price of heating oil, which was one of the mainstays for heating homes in the wintertime across the northern tier of the United States. So what do when you get cold and energy is really expensive? You want to put on a blanket, right? Put on a sweater, put on a shirt, a jacket. So we went in and we began to retrofit homes and add more insulation. All that works well. All that's good. Everything's fine. We warm up our home, we use less energy, and we're a lot more comfortable. But there's another little bit of physics that we have to understand, and moisture moves from hot to cold and wet to dry. So we have all this moisture in our air, and we have moisture from showers, we have moisture from cooking, and the average family of four produces almost 1,100 gallons of water vapor per year inside our homes. You've opened the refrigerator, perhaps, maybe you've had some children in your home and somebody drops a half gallon of orange juice or a gallon of milk and it goes across the floor. It's a mess, right? Anybody ever have a washing machine hose break? Catastrophic, right? 25 gallons of water spilled across the floor. But what are you going to do with 1,100 gallons of water in a year? Well, there's a little bit more physics that we have to understand. We have air movement as well. And air is driven by several different things. We have the wind effect. If you've ever been sailing, you know about the windward side and the leeward side of the sail, right? So we have wind will push on one side of the building and it'll actually suck on the other side of the building. We have the stack effect, that warm air rising, the warm air being more buoyant and less dense than cold air. And that warm air rises, it leads out through cracks and crevices at the top of the building. And it's replaced with cold air coming in down at the bottom of the building. Then we have things going on like combustion and ventilation. And those are our bathroom fans, our kitchen range hoods, our clothes dryers. All of those are big exhaust fans that are sucking air out of the building. And where is that air coming in to replace it? You know, so we have to pay attention. So we've got all these driving forces for air. Well, air carries moisture. So we're back to the moisture. Moisture moves from hot to cold, from wet to dry. And when we have these driving forces, we've got water vapor in our air. And this shows all kinds of different places where we can lose air out the top of our building. We have our bathroom vents and kitchen vents. We have chimney penetrations. And if you've ever looked at a chimney penetration from the top, you can see big gaps around it because you don't want your chimney in contact with combustibles, right? So the code says you can't put wood in contact with a chimney. You have to leave a space. Well, a lot of times those spaces don't get sealed and there's a big air penetration. We have plumbing stacks for venting. We have joints at interior walls and joints at the hatches in the attic and light fixtures and joints between the walls and ceilings and windows and vapor barriers and all kinds of different holes in our buildings. And our holes in our buildings allow moisture driven by air, carried by air, to leave the building. Oops. And what happens then is this, you know, when it's cold in the wintertime, this is a picture I took inside an attic, not outside. This is inside an attic from all that warm, moist air rising into the attic, hitting the first available cold surface, condensing and then freezing. And so you think about where does all this moisture go when it warms up and you have a little bit of weather like we've had the last few days. All that's going to drip back into your insulation. What happens to wet insulation? It doesn't work so good. This was a picture that I took in Selawik, and there was a garbage bag right on this area right here. And that garbage bag condensed a whole lot of moisture on the bottom, and you can see this wire right here that goes down to a light fixture down below. I noticed there was a problem because the light fixture was about 2/3 full of water, and the light bulb was actually in the water. The electrical part fortunately wasn't, but still I realized there was a problem. Went up into the attic, found the garbage bag, moved it, and took this picture. This is another shot of what happens to moisture that goes up. We put vents in our attics to make sure that that moisture leaves. But if it freezes up, you know, there's only a little bit of a hole here for moisture to get out. All the rest of this is closed up by ice. And so not much moisture is leaving that attic, right? So we've got to, actually the better thing to do rather than trying to vent it out after the fact is to stop it from getting up there in the first place. This is a picture I took down in Wrangell. And you can see here that it's a double pane window, and this inner part of the pane is missing, and it forms a nice little aquarium down here. And you know, who knows what you could grow in there. I imagine there's lots of opportunities, but that's kind of the amount of water that we're talking about, you know, just from condensation. So if we've got condensation going through all these little penetrations and cavities, and it's going into our insulation and soaking it, that's not necessarily a good thing. So what we want to do is we want to seal this up as well as possible. And we do that by putting a vapor barrier on, and then we tape any holes, any cuts, any seams, and we try to seal it up so that it holds together and prevents moisture from getting into the insulation, because air carries moisture. So back into Mama's house here, we put a vapor barrier on the warm side of the insulation in cold climates, and now we've stopped moisture from getting into all these penetrations. We actually also have to do a lot more work going in and kind of making sure that we seal all these creations. So there's a light fixture. We want to take some sealant foam around the wires, around the box, the junction box. Here's the chimney that I mentioned. We can cut little bits of roof flashing to go around that on either side. We've got recessed can lights. We want to make sure that those get sealed up well. And there's lots of different ways we can do this. So as we do all this, we can stop that moisture flow from getting into the attic, carrying into that warm, moist air in the first place. So we seal the house, we seal the air leaks, we're doing good. And this is all because relative humidity, humidity in the air is, we call it relative humidity because the amount of actual moisture in the air changes with the temperature. And warm air can hold much more moisture than cold air can. And when air cools, its ability to hold moisture diminishes drastically until all of a sudden we hit what's called the dew point, and then it begins to condense, and we get water changing from vapor form into liquid form. So change the temperature by 20 degrees, and we either double or half the relative humidity. And this works both ways. So if we've got 70 degrees at 50% relative humidity, the dew point is going to be somewhere around 50 degrees. Is it ever colder than 50 degrees in our buildings? Yes, it is. So we can, if we have warm, moist air leaking out, we can have these condensation events. The other way to think about it is if we've got cold air and we're bringing it into the building and we're trying to heat the building, we take 20-degree air, that's even 100% relative humidity, and we heat it to 40 degrees and it's approximately 50%. We heat it to 60 degrees and it's 25%. We heat it to 70 degrees and somewhere around 15%. And that's enough to get sparks when you pet the cat or, go open the refrigerator. You'll zap yourselves. So we can go both ways. So we want to be able to manage that appropriately. We also need to make sure that we take care of all of the bulk water, the liquid water that's coming at our buildings. So we have things like roof leaks. We don't want those. Obviously, that's one most of us would take care of right away. Siding leakage, not so obvious. Groundwater seepage, a lot of our crawl spaces are really, really wet. And we also have this thing called capillary action, which allows moisture water to flow upwards beyond gravity. And you can see this illustration with paper towel. The towel is actually changing to reflect the colors of the water, the dye in the water. That can happen in concrete walls as well, as moisture can be drawn up those concrete walls and enter into our building. So we want to make sure we put sills on the top of the concrete before it gets in contact with the wood. Then we have things like sweating pipes in the summertime. Often in August and September, we have very high outdoor relative humidity, 70, 75%. And our groundwater comes out of the ground at 38 degrees, 40 degrees out of our wells. A lot of us are on wells. Even city water is pretty cold. So we get condensation on our pipes. And we can get a lot of sweating pipes, and that can start dripping. And it's amazing how much water can pool up. If you don't have a proper mixing valve on your toilet, your tank can condense and you'll have water all over the floor in your bathroom. The other thing that happens quite frequently is here we'll see water drips off the edge of the roof. You can see the drip line right here. And the water stains, in a heavy rain, this wall is about 8 feet tall. And so you can see, the water stains are going up probably almost 6 feet. Well, when the water's coming down, from above and coming down in this direction, the siding actually sheds pretty well. But when the splash is going up in this direction, it can go right in through those cracks and get down behind the siding, and that can cause problems. And so this is a picture I took down in Southeast Alaska, and you can see the logs all rotting out there.
Get a little overlap going.
You can see the logs are all rotting out here. And that's because the splash off the roof is coming up and just soaking these logs, and they're never getting quite a chance to dry out. So we want to make sure that we don't build our houses like these guys are dressed. You know, here you've got this guy, he's got his hat into his jacket that is tucked into his bibs, and his bibs are tucked into his boots. So if the water hits his head, it's going right into his boots, right? We can't rely on pookie tape and goo. It doesn't work. You know, this, if he gets water over the top of his bibs here, it's not going to work. So we can't rely on pookie tape and goo. We want to make sure that we have proper flashing all the way up the building, so that we start from the bottom and we work our way up. You think about how we shingle a roof. We start at the bottom edge of the roof and we overlap sufficiently for the climate. We do that with our siding. We also want to allow in our maritime areas like Homer, Seldovia, Seward. We want to make sure that we have a little bit of space behind the siding, so that we can have a little bit of place for drainage to happen. And then finally, we want to make sure that when the space does get wet, it has a chance to dry out. So we put this vapor barrier in, we deal with our bulk water problems. We've got our insulation level in, and all is well and good, except the moisture buildup can cause things like mold and rot inside the home. So we want to make sure that we don't do that. In order to keep that to a minimum, we want to put in a good source of ventilation. So even just a simple bathroom fan at 50 cubic feet per minute run, 12 to 16 hours a day is sufficient. And if you're a single person or a couple of people that aren't in the house that much, you probably don't need to run it that much. But if you're a family of 4 with pets, you probably want to run it more often. So we want to make sure that we put ventilation in, so that we can create enough fresh air and exhaust the moisture and the odors, so that we can keep our building's relative humidity somewhere between 30 and 50%. That's about optimum for humans. 30% is not so dry that you're going to draw sparks when you pet the cat or open the refrigerator. And 50% is not so humid that it's going to cause lots of problems if it does escape and condense in the rest of the building. But if we seal up the whole building very tight and we start exhausting air out of it, where does that incoming air come from? Well, in our previous existence of heating systems, we've had heating systems that just drew air from the room, usually to provide combustion air for the heating system. And if we get all that air leaving the building, all of a sudden we can start getting air drawn down the chimney, and if it does that, then it can start spilling combustion gases into the living space. And those combustion gases can be nitrous and sulfur oxides, as well as carbon monoxide, which is, all 3 of those are not the sort of things that we want to be breathing on a regular basis. So this illustrates the concept of backdrafting. We have air exhausting out of our range hoods, out of our bath fans, out of our clothes dryers, and it could potentially draw air down the chimney and through our furnaces, boilers, water heaters, etc., and cause problems. These are some pictures that I took of improperly vented or unsafe situations. If you look at the center picture, you can see a lot of black soot around the draft hood, and that is strong evidence of backdrafting. That's drawing soot out of the out of the combustion gases, and it's depositing on top of a water heater. The upper right picture is these water heaters are designed to vent because warm air is more buoyant and less dense than cold air. So warm air rises, but it doesn't go downhill very well. And then the upper left picture is a little bit challenging because while these elbows are all able to be straightened out, every time you put an elbow in a vent pipe, it's the equivalent of about 10 feet. A 90-degree elbow is the equivalent of about 10 feet of straight pipe. And I counted 13 different elbows in this picture to go about 8 feet. So it's the equivalent of 130 feet to go 8 feet. All of this is improper venting. It's not going to make the water heater draft very well, and the likelihood of spilling combustion gases into the living space is high.
Why would anybody do all those?
Who knows?
Yeah.
Experimental architecture.
Okay.
So the upshot is, when we are adding ventilation to our homes, we want to make sure that we put at least one fresh air intake that's the equivalent of the amount of air that's leaving the building, so that we can draw fresh air into our building while we're exhausting the odors and the moisture through our mechanical ventilation. So a simple bath fan like this one, it draws about 13 watts in an hour, very inexpensive to operate. The little item on the left there is called a Fresh 80, and that pops open and closed so that you can have fresh air come into your room as you're exhausting with this fan. So that's a good system. We have air exchangers that will actually draw air through ductwork into the building, through the box, and then exhaust it into the home. And then we have what's called a heat recovery ventilator, which actually draws the heat from the air that's leaving the building and transfers it to the cold air that's coming into the building. And we get that heat exchange. And so we're actually bringing warmer air into the building. So a house is a system. We want to make sure that we build it tight and ventilate right. So the last thing we need to know about our building science for this evening is heat transfer. Heat transfers through three methods. There's conduction, which is if I put my hand on a flat surface and I hold it there for about 30 seconds, and you can try this. You can put it up, put your hand on the table nearby you and hold it there for about 30 seconds, and then move your hand away. And when you move it back, you'll actually feel the warmth that transferred from your hand to the table surface, right? So that's conduction. Your hand is warmer than the table surface. Heat moves from hot to cold, so you conduct the heat into the table surface. And we do that in our homes as well. Convection is that principle of warm air being more buoyant, less dense than cold air. And so warm air rises or warm water rises, and cold air or cold water falls to the bottom. We see that in our lakes. We see that in the ocean. We see that in our homes. And then the final one is radiation. That's one like a wood stove. If you stand next to a wood stove, the heat that's coming off of that wood stove is radiant heat. And we also have radiant heat in our floor system. Sometimes we use what's called radiators, right? So it's radiant heat is transferred, and that radiant heat moves in the infrared spectrum. It moves equally in all directions. It's line of sight only. So if there's a big sofa in front of the wood stove and you're sitting on the other side in a chair on the other side of the sofa, you may be a little bit cold, but you move that sofa out of the way, and now even if you're all the way across the room, the wood stove you're gonna feel the heat from the wood stove because it does move in line of sight. It doesn't really warm the air in and of itself, as air is a poor conductor. Again, the thing that we want to make sure of, though, is that we are safe with our heating systems. The barrel stove on the right is one of the more unsafe systems that I'd ever seen. There's no heat shield, galvanized pipe, no ceiling jack. That's a fire in waiting. What you really want to see is a lot more of the type of thing is the picture on the left, where you have a good ceiling jack with black pipe going up, presumably connecting to thermally insulated pipe going up through the rest of the building and out the roof. You've got, you've got a heat shield behind, you've got heat shield underneath, and you want to make sure that our systems are safe. And I'll show you a couple other pictures of unsafe furnaces that I got to see in my 30 years of going into different people's homes. So what do we want to do when we've kind of gone through the basics of building science and understanding how heat, air, and moisture move through our homes. So what does that mean when we want to make improvements? Well, the first thing we want to get a hold of is the air leakage. The air leakage is really important. And then we're going to go to the heating system, insulation, water heat, electrical, and finally, doors and windows. Many people start with doors and windows, and then they wonder why they still have problems. Do all the other stuff first. Then if you still have problems, you can do the doors and windows. So again, we want to be safe. Our heating systems, this is a picture I took in Fairbanks, and I was rather astonished at the ingenuity. That's an old wash tub underneath the furnace itself. And they just cut a couple of holes in it, and they used some flex dryer duct to provide heat to different parts of the house. And, you know, the funny thing was it worked, and it really wasn't tremendously unsafe, but it wasn't very efficient. So if, you know, we should be having our furnaces and boilers tuned up and cleaned at least every other year, if not every year. And they can easily do an efficiency check on them. And if you're not coming out better than 80% efficient after it's been cleaned and tuned, you may want to consider replacement, because new furnaces, new boilers for oil are usually 87 to 89% efficient, and gas furnaces are upwards of 95 to even 98% efficient. So the other thing that we want to look at is the way that we get our air intake. So if we have what's called a sealed combustion boiler, we're drawing our air in the bigger pipe on the bottom here, drawing that air in from the outside, or that would actually be the exhaust pipe. The air would be coming in on this curved pipe on the intake, and then exhausting out the bigger pipe on the middle of the bottom of the picture there. And so we're drawing air in from the outside and exhausting it back to the outside. We're not using the living space to provide combustion air. And the advantage of that is no matter what happens in the combustion, in the living space, we're not going to have that backdrafting situation that I described earlier. So space heaters like monitors, Toyos, Rinnai, these are all used in smaller homes that have a more open floor plan. Sometimes you may need a couple of these, but they work really well, and they can work just fine. Again, they need to be cleaned and tuned at least every couple of years, if not every year. And if you have a furnace where you're moving air through the building, the next thing that you really want to pay attention to is seal the ductwork. You know, and there's mastics and good quality tapes. Do not use duct tape. The Lawrence Livermore Laboratory did a study on sealing ducts with duct tape, and they found that it failed reliably and catastrophically whenever used on ducts. So mastic and high quality duct sealing tapes are much better. And then again, we want to make sure that it's vented properly. again, this is in Fairbanks, and the moisture coming out of the combustion process is just collecting all up under the eave of this house. And it's actually an unsafe situation because a little bit of a thaw and that ice is going to let loose. And if there happens to be somebody out there at the time, that's a big headache. So heating systems, again, we want to clean and tune at least every other year, preferably every year. We regularly need to change our furnace filters depending on how dusty and how much pet hair and people hair you may have. Seal the ducts with mastic, not duct tape. Vent it properly in safety. And if you have a wood stove, please, please, please get those chimneys swept often. Insulation is the next part that we want to go after, and there's a number of different ways that we can do that. In this picture, we're looking at drilling holes between each of the floor joists, between the lower floor and the second floor, and we're actually blowing cellulose insulation into the cavity there. And then we put plugs back in those holes and put the trim board back on, seal those plugs, and we can have a nicely insulated floor. Oops, I went the wrong way. There we go. Another way we can do it is if we happen to be able to pull the siding off, we can then go in and insulate from the outside. That helps in that we don't disturb the living space and we don't disturb the occupants, and we can get a good seal and a good vapor barrier on the inside. But then here we have my buddy Phil blowing cellulose and new construction into wall cavities as he was building his house up on the hillside in Anchorage. And with insulation, we have 4 climate zones in Alaska. We range from climate zone 6 to climate zone 9. And 6 is in southeast and south central Alaska, where we want to have our walls minimum of R21 up to about R40, crawl spaces minimum of R10, ceilings about a minimum of R45. We don't really want skylights because that causes a lot of roof melting of snow and ice on the roof, and that can cause a lot of other problems. Doors to about R7 and windows to about 3.5. Water heat's kind of the next one. So water heat, particularly if you have a family, we have a lot of people taking showers, a lot of cooking going on. We can use a lot of water. So we want to make sure that we have a good sealed combustion water heater that is going to be relatively efficient. Older style water heaters were about maybe 50 to 55% efficient. Newer ones can be about 80% efficient, and maybe a little bit more if they're connected to a boiler. But one of the things you can do, regardless of what kind of water heater you have, is to put low flow shower heads with, and maybe with a shutoff. Older style shower heads used to use about 5 to 6 gallons per minute, and newer ones are 1.5 to 2.5 gallons a minute. And if you think about somebody taking a 15-minute shower at 6 gallons a minute, that's almost 100 gallons. Yeah. You think about 1.5 gallons for that, and it's probably more like 10 gallons, if I did my math right. So then also blanket on a water heater is good to insulate it so that it's not losing all its heat when it's on standby. We don't need to set our water temperatures up above about 120. A lot of people used to set them around 130 to 140, and that was really way too hot. My grandmother actually got scalded by water coming out of the tap. She had a little bit of a mini stroke while she was washing dishes one day, and she left her hand under the tap, and she actually scalded her hand because her water heater was set too high, and it doesn't need to be set that high. We can wash our clothes in warm or cool water, and use sinks to wash dishes rather than let the water run. Refrigerators, newer refrigerators, we can get newer refrigerators under 500 kilowatts a year. We used to be spending anywhere from 1,300 to 2,000, even 2,500 kilowatts a year for refrigeration, for one refrigerator. So we can save a lot. And then the other thing with refrigeration is know what you want before you open the door. You know, don't stand there and go, oh, let's see what I want to eat now, you know, and stand there with the door open, particularly in the summertime. And this is just a little life cycle analysis I did. You know, say you had your refrigerator dies on a Friday night. And you're like, oh, stores are closed. I can't get one till Monday, even if it is possible. But your neighbor says, oh, I got an old refrigerator in my garage. You can have that for $50. You say, great. Well, you get that one. It uses 2,500 kilowatts a year. It's going to use it's going to cost you almost $1,300 if you keep that for 5 years. If you go out and buy a new one that's in around the 500 kilowatt a year range, even if you pay an exorbitant interest cost, you know, you got a high interest credit card, you're still going to come out ahead and save about $325 a year over an old refrigerator that somebody gave you for $50. So do a little life cycle cost analysis. If you got a refrigerator that's more than about 15 years old, consider replacing it because it'll save you some money. Lighting is definitely a big plus. If you still have incandescent lights in your house, there's no reason to. There is no reason to have incandescent lights in your home anymore. Replace them with LED bulbs. You can get LED bulbs relatively inexpensive. You can get them in any color temperatures. You can get them from very warm white to very cool. If you don't like the color, it's usually because you've got the cheapest ones that were available, and those are about those are actually called daylight bulbs. And so you really want to get the warm white ones that have a color temperature of less than 3,000 degrees Kelvin. Fluorescent tubes, T8 or T12, can be easily replaced with LED tubes, and that can save you up to 60% per fixture on fluorescent tubes. You know, there's no reason not to have LEDs in our house. We use the compact fluorescents, the bulb on the right in the picture there. For a while, they used about a third the energy that an incandescent bulb did, but the LED bulbs are only using about a fifth the energy that an incandescent bulb did. And like I say, you can get them in any brightness and color temperature that you want, and that'll help you know, mitigate anything. The nice thing about them is, particularly if you have light bulbs that you have to climb ladders to change, is that you go up there and change it now, and you probably won't have to change it again in your lifetime. 10,000 hours of light is an awful lot of hours of light. And we don't run our light, you know, 24 hours a day. And here in Alaska, we don't even use a lot of our lights in the summertime, you know, for several months of the year. So, but that's, you know, just the cost of replacing incandescent lights with LEDs, or replacing an incandescent bulb every time it burns out, you're going to spend more replacing incandescent bulbs than you're going to spend on a new LED bulb. And that's regardless of the energy savings. So, and the hassle and aggravation when a light bulb burns out, when you want it and you don't have another one, you won't have to worry about that if you're using LEDs. Doors and windows, we've got, we want to make sure that we have good quality doors. We want to use insulated doors for our outside doors, not interior doors like this one that frosted up a little bit. We want to prevent ice and water buildup on the bottom of the windows. We want a good quality window that's going to prevent that. That's a combination of having a good quality window and making sure that the humidity in the house is not too high and that we've got plenty of ventilation like we talked about earlier. So windows and doors, we do everything else first: air leakage, heating systems, water heat, lighting, appliances. We do that all before we get to the doors and windows. If you are going to buy windows and doors, use good quality frames. If you can get insulation, that's better. There's what's called a warm edge spacer. If you look at a thermopane or a triple pane window, you see a little metal strip holding the panes together on the side of the window. If you can get warm edge spacers, that's a lot better than just the plain metal. Get the best you can afford. Spend a little bit more because you're only going to do it once. And you want to get an R value of at least 3.5, which equates to a U value of 0.26 or less. The U value is just the inverse of the R value. And if you're on new construction, put most of your windows to the south, less on the north, because passive solar works really, really well here in Alaska. So with that, if you're looking for more information, the Alaska Housing Finance Corporation Research Information Center has a whole lending library on energy efficiency. And here's the link there. It's ahsc.us/energy/ric.cfm. And it's really helpful. Energy efficient homes, when we get them right, are going to be healthy. They're going to be safe and comfortable. They're going to be a lot more durable, free of mold, rot, decay. Paint's going to stay on better. We won't have roof ice. Roofs will last longer. Gutters and fascias will survive the winter, and they're going to be a lot more comfortable. Even temperatures throughout the home, draft-free, quiet, less dust, not cold near the windows, humidity levels where we want them to be and able to be controlled. And we can control pollution that happens in the home in the form of radon, smoke, odors, and that sort of thing. And finally, they're going to be affordable. You know, you can get energy efficient. If you do an energy efficiency retrofit, you can refinance and you can save up to almost a point on a 30-year loan. It's definitely going to lower your cost over the life of the home. It's going to lower your maintenance costs, fuel and electric costs. And arguably, if you've been in a home that has a lot of internal contaminants, you're going to have lower healthcare costs. So, and then we have the societal benefits of lower greenhouse gas emissions, decreased resource extraction, frozen pipes, minimize, and reinvesting our energy dollars in the local community. So it helps our local economy as well. There are a few programs that are available for low-income people. The Weatherization Assistance Program, the Alaska Community Development Corporation in Palmer actually serves the Kenai Peninsula. Their phone number is 907-746-5080. They're alaskacdc.org. There are federal income tax credits through Energy Star. And if you look at the Energy Star website, you can find out about the federal tax credits. And coming in 2023 is some new form of a home energy rebate program. And also a low to moderate income appliance rebate program. And it'll somehow be based on energy savings, but we're not quite sure yet how that's going to be. There's going to be a solicitation, public comment federally for in January on how to manage the program. So if you have ideas or comments, probably talk to somebody at Alaska Housing Finance Corporation about that. But it won't roll out until probably next fall, 2023 at the earliest, and it may be even a bit later. So with that, we have our home that has a nice warm insulation blanket. It's got a good vapor barrier where we sealed all the air leaks to prevent moisture and air from escaping the building. We put in controlled ventilation with fresh air intake that exhausts odors and pollutants and moisture out of the home. We put safe sealed combustion heating systems in, and we put a carbon monoxide indicator, which is required by law, but it's also a really, really good idea. Then we have a very energy efficient, affordable, healthy, durable, comfortable, safe place for us to live. And with that, I'll take questions. Anybody have questions?
So I can go ahead and this is kind of our weird experiment with a combined event, a hybrid event here. So I'm actually even going to ask Scott to use the raise hand feature for his audience there too. And so yeah, does anyone have any questions? Go ahead and either just turn your video on and raise your hand, or use the raise hand feature in Zoom. Or if anyone here wants to raise their hand.
Okay.
Right, go for it.
We got a question here. I can't get the microphone over and raise the hand feature at the same time, so.
I have a question that dealing with a specific HVAC ventilation system. So how often does the ductwork need to be cleaned, and who does that sort of thing? This is one of those ones where it has those round circular vents in the rooms, and you can unscrew them and look in and see if they're clean or gunky. And,
Yeah.
but what about the stuff behind them that you can't see in the walls?
Do they look gunky?
Yes.
Okay. Normally, the question, if anybody didn't hear it, is how often do heat recovery ducts need to be cleaned? And that would really depend on what's causing them to become dirty in the first place. How often, there are duct cleaning services. I don't know who does that here in Homer. But if you're getting a lot of buildup, then that leads me to believe that you're probably getting, there's some source of contamination that's nearby, either in the house or just outside, that's causing a lot of dust. And how often it needs to be cleaned, it's hard to say. There isn't any rule of thumb for that. It's when they get dirty, but if you can put filtration on to prevent all that dust from getting into the system in the first place, make sure that the filters get changed regularly, that would be the best thing for minimizing that.
I had a question. You've kind of defined the system, the house system, and done a really nice job of bringing all these things together. What do you see as far as emerging technologies like heat pumps? How does that change how we might think about that system?
So the main thing that things like heat pumps would bring to the table are that they are non-combustion. So if you put non-combustible heating systems like a heat pump into the home, then you no longer have to worry about all of the backdrafting and carbon monoxide issues that you might get from combustion appliances like natural gas or oil or propane or wood. So you can you have the benefit of that. If you're comparing the cost of a heat pump to fuel oil, that probably works pretty well. It's going to probably be less expensive. If you're comparing it to current prices of natural gas, that could be a little bit more expensive currently, but who knows what the price is going to do in the next few years as these gas contracts begin to dry up, and there may not be as much gas available, and if there is, it's likely to be a lot more expensive. So I think there is the very real possibility that we'll see heat pumps be able to compete economically with natural gas very shortly. Other things on the horizon, there are more on a utility scale, not for in-home use, but we have geothermal and tidal and some things on the utility scale But most of those things are not gonna be available for the average homeowner. I don't really know of a lot of, there's new materials that come out all the time. There's aerogel windows that are starting to be sold commercially now that have a much higher R value. There's windows that can change their tint based on how bright and sunny it is outside. Again, they're available commercially, but they're pretty expensive.
And what about heat recovery ventilation or similar systems?
Yeah, those systems haven't really changed or made that much improvement, you know, bits and pieces of improvement in efficiency over a number of, you know, years, but you know, the main technology for that has been around for a couple of decades.
Thank you. Any other questions out there? You got a question?
Yes. The tubes, like why were the bends in the tubes equivalent to a lot of length?
So we have a question about why do corners in ducting, why is that equivalent of having much more length?
It's just basic disturbance in the airflow. If you get air moving in a direction and you have to put a turn on it, it's sort of like driving a car or riding a bicycle. You may have to slow down to make a sharp corner. So it's the same principle when you get air moving down a straight pipe and you have to make a sharp corner. It just takes more effort to make that corner.
Any other questions out there before we adjourn to our local events for those of us who are in person in various places?